Hello everyone, I am Oshin. Today I would like to talk about switching loss.
You might heard electrical appliance consumes power even it is not used.
It's because the PSU consumes the power by itself. One of the factors is switching loss. To measure the switching loss, it is not easy as using a multimeter. For accurate measurement, I use this advanced oscilloscope model GDS3652A. Correct measurement also requires professional knowledge. Here are so many tricky parts. One will introduce them in the rest of video. Today I will use this AC to DC power converter module to be the DUT, which is taken from a DVD player. This main transistor is our target for measuring switching loss. It is the heart of switching mode power supply. Let me introduce switching loss first. When a general transistor is working on switching mode between on and off, the waveforms look like this.
In the off period we have maximum voltage and minimum current. In the on period we have minimum voltage and maximum current.
The transition edge waveform between on and off states isn't perfectly vertical, usually showing a noticeable slope. It looks like this. Here is a slope.
The switching loss is just here.
By multiplying the voltage and current waveform, we can find distinctive pulses in this area. This is the power of switching loss. It is the power we lose. Here we have T on. And the T off is over here. The waveform here looks so smooth. But in AC-DC switching mode power supply the waveform will be a little bit different. It looks like this. This is SMPS's waveform. That is because the transistor connects with diode and capacitor. All of them interact to each other and come out this complicated waveform. The waveform looks so particular. Please keep it in mind. When you see the real waveform later you will recognize it. Here is the SMPS schematic diagram. The primary path that the current follows is represented by the red line.
To get the switching loss,
in order to calculate the power, you need to multiply the voltage VDS of the transistor with its current IDS. Is it easy to measure these values? Not at all. You can either spend some money to buy a differential probe and a current probe, or you can use some tricky tip to do the measurement by a general voltage probe. Why do you need differential probe and current probe? Because of the primary side of the electrical transformer. Its ground is hot ground, whereas the oscilloscope's ground is cold ground. If hot ground and cold ground are connected, the circuit blows out. To measure the primary side component voltage accurately, we need a differential probe. This is the formal way.
Regards to the detail about hot ground and cold ground you can watch the video at top right corner.
Next topic is current IDS.
We need a current probe.
This is an expensive device. Even the differential probe I mentioned is expensive too. Basically you won't buy these expensive probe if you try to measure the switching loss by just curiosity. How do you measure the switching loss by using this general voltage probe? It is tricky. All you have to do is cutting the ground wire of oscilloscope. Ground lifter can help you to do this. Now when we connect the oscilloscope's ground to the hot ground, the scope's ground becomes hot ground now. Then we can measure the VDS accurately. To accomplish this, we absolutely have to take some level of risk. Any exposed metal of the oscilloscope would never contact any cold ground. Otherwise the DUT will blow out. People may say, how about removing the ground prong of the plug, to prevent the circuit blowing out? It will be much easier. Oh, no way. It is solely for this particular case to cut the scope's ground. In the case to measure the PSTN phone line, the scope has to be grounded. You can check the phone line topic at the upper right corner. We have to use different setting for different situation. Next, how to measure the main current IDS. If you don't have a current probe, you can use the shunt resistor method.
You have to put a low resistor in the current path.
I placed a 0.5 ohm resistor using two parallel 1 ohm resistors. By probing the voltage across the resistor, we can accurately measure the electrical current. I must adjust the scale to the situation, with the voltage to current conversion factor set at 2. How to put this low resistor into the current path? If there is no shunt resistor in the original designed circuit,
you need to do a lot of work.
This is the case I faced. Let me show you. To reorganize, I relocate the transistor to a more suitable location. Next, insert the shunt resistor into the designated path. The two 1 ohm resistors yield 0.5 ohm. Next, I carefully connect the remaining wires individually. Thick wires are for high current and thin for low current. To prevent any potential interference, I carefully twist the wires together. The whole procedures took some time. Now I think everything is ready. We can start to measure the switching loss for this power module. Let me remind again. I connect the hot ground of the power module directly to the ground of the oscilloscope. Ensure that every single ground of oscilloscope is properly and completely isolated. Including the connectors of the oscilloscope, they cannot connect to other instruments. Alright, at this moment, let's proceed to turn on the crucial power module. What you are currently observing is the waveform of the voltage and the waveform of the current.
I have introduced the waveform previously, now you can see it. The yellow trace is voltage waveform and the blue one is current. Let's tap the power analysis menu, then select switching loss.
Okay.
Now we have additional red trace here.
This is the power which is the result of multiplying voltage and current waveform. The pulses that are present here fluctuate between the on and the off region. This is the switching loss.
This is a 650 MHz scope.
Let me try to scale up the waveform. Scale the waveform up. Can you see it? This is the switching loss. The waveform isn't jagged. It looks like some kind of HD screen because wide bandwidth. All measured results show on the screen. You may observe the field is blank. Sometimes this phenomenon relates to reference level, since the waveform of SMPS is complicated and individual. So we need to set reference level additionally. Then the scope can determine the timing of T on and T off. Let's scale the waveform to a proper size by turning the horizontal knob. Press single. After single stop. We got a beautiful waveform here.
Let's take a look at the reference level menu. There are 3 level settings: high, middle and low. The waveform's highest level is 100%. The lowest level is 0%.
Let's start from low reference level. The default value is 5%.
Low reference level is used to avoid interference by noise.
Set the low level to 5%, make it above the noise. Next, high reference level.
The default level is 90%.
It is recommended to set the value at the end of the raising part of the trace. But you still have to find a proper value by try and error. In my case, the setting is 47.6%. So you have to try and error. Next, middle reference level. There is no specific rule for it. It is used for aiding oscilloscope to find precise timing of T on and T off. The key point here is to avoid the oscillating region or the oscilloscope will be confused. For me, I set the middle level at lower level. In my case, the setting is 20% or 12%. Once the reference level setting is done, the result of switching loss shows up. Let's think about the calculation period. Does it calculate just one switching cycle or many cycles? Actually, it depends. So here is an option called gating. You can decide which segment of the waveform should be used to calculate the switching loss. It is like flash sale. People enter the shop only when the door is open. Once the door is closed, people stop. For example, gating off. Let's check the gating menu.
The idea of gating off is kind of convenience store.
It opens 24 hours. A welcome sign is always there, means there is no gating. It just calculates the power of whole waveform. The next option is screen. Gating screen runs calculation only in the period of the displayed waveform. Here is a red sine wave. It presents the whole waveform acquired by oscilloscope. The white rectangle represents the displayed waveform on the screen. So the waveform on the screen is just a part of whole waveform. Gating screen runs calculation only for the displayed waveform. Next one is cursor. Between cursor. Between cursor allows you to set two cursors just like the cursor 1 and cursor 2 here.
Oscilloscope calculates between two cursors.
This option is flexible. You can set the period between cursors. I think these three options are useful for most cases. Next, let's see conduction loss. I mentioned switching loss previously.
Switching loss is the transistor power loss in T-on or T-off period.
By multiplying the voltage and current waveform, the power loss between T-on and T-off is called conduction loss. It is the power loss when transistor is turned on.
To get the conduction loss, let's check the menu.
Here we have the conduction calculation. You can set the conduction calculation to multiplying voltage and current waveform. Or you can set the conduction calculation to RDS. If the transistor is MOS FET, you can set the RDS as a parameter. Let's select RDS now. You can adjust the RDS value. In my case I have 0.154 ohm.
By setting this parameter,
we've obtained the conduction loss power. The loss energy is displayed here. If the transistor is BJT, you can set VCE in saturation mode. For example, I set the VCE to 103 mV as parameter. The energy and power are shown here. So, you have many different options to get power loss.
There are many indicators for examining a power module.
That's why there are so many test items in the power analysis function.
I will introduce other items next time.
Today I introduced how to measure the switching loss of the power supply. Like me, if you're using a general voltage probe, there are numerous tricky things to do measurement. Of course, safety first. This kind of operation requires more preparation and risk management. Okay, I think the video is about to end. Don't forget to subscribe Strong Pi Lab channel.
Goodbye.